Hey guys, I'm going to save you the webcam for this one here. So I just made the video evaluating your data, your lab equations. You're going to have to do that for your own two videos. So you're actually going to have four equations: position versus time and velocity versus time for two of the videos. I think I said three videos in the weekly plan, but I only want you to write up two of the videos and kind of compare whether or not one person achieved a better constant acceleration than another. So I'm going to guide you through the lab write-up, kind of read you through this, talk about the equations, kind of what I expect you to do. Yes, it's a PDF file. If you copy and paste it into Google Docs, it doesn't look great. So I do want you to retype this, but once you do this once, then um, it'll be good to go. And yes, I do want you to copy this format, right? For Physics C, you're going to put AP Physics C up here, your name, date of the write-up, or date of the lab. So um, for my first section, you could put today's date, which is the 22nd. Uh, Fun fact, it's also Bilbo Baggins and Frodo Baggins' birthday today. Uh, literary literary heroes. Anyway, um, so lab title, Physics C, I would call this um, constant acceleration video analysis lab, something like that. Constant acceleration lab, kinematics lab one, whatever you want to say. The purpose here, all right, this is often determine a relationship between one variable and another variable. In this case, we're doing the second option here, specific tasks as specified by teacher. Purpose here is to determine whether or not um, a physics lab student could act out constant acceleration motion or constant accelerated motion, however you want to say that. So again, the task here was to determine whether or not a student could produce constant acceleration motion. The materials, okay, we had the tape meter, the meter tape. We had three cones, a tripod, a cell phone, and then physics students. The apparatus, a drawing goes here, okay? If we do it in school and you can take a nice picture of it, you can take a picture of it and label the picture, all right? So you're gonna put, probably leave a little space in here and draw it in. Now keep in mind, you have to list the materials. So list the materials right where this text is, just list those materials I just mentioned out right there, and then label them in your drawing when it goes here. So leave space for it. You can print it out and draw it in after the fact. Procedure, this is a number list of each step. Indicate if certain steps are repeated. Keep it basic, one step per number. Don't try to write too much for each step. Okay, this is like bare bones. Here's what we had to do. All right, evaluation of data. This takes up the most space in your lab. All right. I'm going to go over to a Google Doc here in a second, and I will show you a bit of how to write this up. First thing you want to do is describe your graphs using a sentence or two for each graph. So, for example, visit first time graph for the accelerating buggy shows the top opening parabola. See graph one. And then you introduce your experimental equations. Your experimental equations go into your evaluation of data. I explained what the experimental equations were in the last video. Your general equations go in the conclusion. Okay, so it's going to be a little bit of repeat there, but whatever. So I would start this evaluation by saying something like, let's see, let me go kind of over here and just do evaluation of data a little bit. Data we produced. I performed or dormed. Oh, it's late. I'm not typing well. I performed video analysis on two physics students' motion. Two physics students attempted constant acceleration motion. Or that's terrible wording, but I'm not going to go back right now. I would think about writing that differently. I performed video analysis and two physics students attempted constant acceleration motion. Uh, in analyzing the graph for student one, see graph one, it appeared, analyzing the graph for student one, see graph one, I applied a linear fit to the velocity versus time graph and a quadratic fit to the position versus time graph. The experimental equations are listed below. All right. Now, I like to make the heading of each area bold. I like to shift this in a little bit. You know, it doesn't give me anything crazy. You got to shift that back just to kind of, you know, make that look a little nicer. The equations are listed below. Now, graph one, hopefully it'll say graph one. If you have to write on your printed graph one, that's fine. You should reference it. So in here now, I'm gonna make an actual equation here. I'm gonna insert equation. All right. Now we have some tools up here. This definitely does not work as well in Google Docs as it does in Microsoft Word, but you will get the hang of it. So first I'm going to do the position, x equals negative 0.40. Now we're going to select here, math operations. No, that's not it. Where are we looking here? It should be it. There we go. Meters, and then I think you have to hit the over arrow. So see these little boxes here? You know, there's not boxes, but that's what you got to fill in, A and B. When you do one of them, to do the next one, you then click the over arrow, meters per second. Now we want it to be squared, so now we have to do another equation function on that seconds there. Great, this is going to be a pain to get in here. Let me go. Okay, the seconds. So before I do that, I'm going to go here. I'm going to select this one, seconds over arrow, and it's going to bring me up to where the 2 has to go. Second square. Then I do an over arrow again, and over an arrow again. That should put me back up on the line. And now I'm going to do the t squared. It's really not as nice as Microsoft, but it is what it is. This is what's free, right? So we're doing another one of these. T, hit the over arrow, 2, hit the over arrow again, plus 3.7. I'm going to do one of these, meters, right arrow per second, right arrow again, T. Oh, brought me out of the equation. Whoops. Over arrow T plus 0.014 meters. All right, cool. I hit the over arrow, I hit return, hit return again, insert another equation. Now, I'm going to do it again now for velocity. I'm not going to, and after this, I'm going to let you kind of do the second equation. 8.5. Then I go up here, meters, over arrow, seconds, over arrow, T plus 3.8, and then meters per second. All right. So there's our two experimental equations. Making general equations is way easier because you don't have to put units in there. All right. Now I would go talk a little bit about what these variables mean. So I hit return. I'm gonna hit tab so it'll line up. So when you hit tab, it'll line to wherever the indent is set up here. All right, it's kind of a nice thing. I'd go ahead and explain these um, equations as we know. I would say something like these functions are in the form of constant, so in the form of constant acceleration, kinematics functions, something like that. Kinematic equations, constant acceleration. Oh boy, what's going on here? Undo. Kinematic equations. Where the term in front of t squared, I should probably do this. T, and then if we want to do a superscript up here, or insert, is it? Insert. Oh boy, where is it? Tools. Come on now. Where's my superscript? Da, 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 da. I just thought it was insert. Oh, I went back in the equation. Insert. No. Where the heck is my? Oh, that's annoying. It's built in here somewhere, but I don't know. I'm not seeing it right now. Why am I not seeing it? You could always insert another equation, but that'd be kind of silly. Oh, it's just killing me. I know it shows it here somewhere. Let me close it real quick. Hide the menus. No, I don't want to hide the menus. Oh man. All right. I'll have to find that later. It should be in there somewhere. That's really annoying. I thought it was just an insert, but I guess not. Superscript, subscript. I'm being stubborn now and I just need to move on. Oh well. Well, I'm gonna get around that by just inserting another equation here. Insert equation. I'll do this. It'll look better anyways because it'll look like it does in the actual equation. All right. Oops. Horrible, Carmen. Horrible. T squared. All right. In front of t squared represents 1/2 the acceleration. Probably should start off by describing actually the fact that the slope of velocity versus time is acceleration, where the slope of the velocity versus time graph represents the acceleration of the student in the y-intercept. Student's initial position. The term in front of e squared in the position versus time graph, half of the acceleration. Then I would say, you could probably say the A term. That would have been a lot easier, right? The A term in position versus time. The B term represents the initial velocity. The c term represents the initial position. So you got to describe what each of these terms represents in the equation. I'll leave you to that. I would report the correlation here of the two lines as well, because that's probably going to be your justification to say which one had a more constant acceleration. So if the curve fit for position versus time has a stronger correlation than for student one, then for student two, you could say that student one did produce a more constant acceleration. So the correlation here, the correlation for position, and you might put that right in the after the equation. You might say correlation. Actually, I probably put it just in the equation so it has the same font. Say correlation equals 0.9999. This one correlation equals 0 negative, and the negative doesn't matter. You don't have to do that. 0.9832. So pretty good. And after you've described what all these variables mean for all these, so you got more work to do here. You got to describe what they all mean. You probably say that I applied the same curve fits to the second student and the following second student's data set, I should say. Data and the following equations were produced. All right, so write those equations now. Report the correlations. You don't need to re-describe what they meant. Now, I'm not going to make any determinations in the evaluation of data. That's kind of the point here, right? The evaluation data, you're just kind of presenting it. What you're giving your equations, you're giving your stuff. In the conclusion, right? When you get going on the conclusion, oh, that's great. Conclusion. What you'll do is first go back to that. First, restate your findings relative to the purpose and tasks. All right. So right here it says, if I gave you a specific question to answer, you should start to address the question here. Describe what aspects of your graphs you're using to address the task, and analyze that aspect and make your statement. Well, I guess in my directions here, I do want you to state what's going on there. So you probably say here, you can see that the correlations for student one, you can see that probably both students produced I guess we should say since both students produced linear velocity versus time graphs and quadratic position time graphs, they both moved with a constant acceleration. The better relations of the two can be considered to be more constant. I'd probably leave it something like that. And in the conclusion, I'd specifically say, again, I'd restate, basically what we saw right here. Both students produced, All right, lightning speed. Ready? Both students produced constant acceleration as seen, as described. Um, Constant acceleration. Produce constant acceleration motion. Student one was slightly more constant due to the better correlation. You want to avoid saying like his or her or whatever. You like want to refer kind of generally to the stuff, and you don't want to say yeah. That's one thing I kind of forget. They often don't want you to say I in lab rapes. They often want you to say like video analysis was performed. Um, so when I that's kind of something I forget about. Video analysis was performed. It's not really supposed to be I kind of forget that. Da, 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 da. A linear fit was applied. The same. Oh, hey, my daughter. Same curve fits were applied to the second student's data, and the following equations were produced. Both students student ones have a better correlation. The following, using what? Using basic definitions in physics. Following general equations were produced. All right. So then you'd do what you did up here, but it'll be the general equations instead of the experimental equations, the ones in green in the previous video. All right. And then the final thing there, so if you go back and look at this, restate your findings, according to new derived general equations using variables, list any sources of error, and at least one improvement that can be made to each experiment. So that's up to you to figure out, right? Do your general equations. You don't need to describe again what they mean. You already defined the general equations up here by describing what each of these numbers meant. Down here, just list out the equations with the letters in there instead of the numbers, the ones in green in the previous video. And then, just like we did here, pick up the writing after it, and say something like, possible sources of error have to do with camera being crooked. That can have a really big effect on this if the camera's tilted wrong. If we didn't set the scale carefully, generally plotting points, right? If someone's points are kind of bouncy, that's tricky. If you have poor light, that's tricky. We did not have poor light in this lab. Let's see, what else? Not setting your origin properly in Logger Pro and etc. Those are all sources of error. And think about ways to improve it. Maybe we try to get a better quality camera on a sturdier tripod. We maybe try to get back a little farther so you're moving more just in the center of the camera, and so on. Lots of stuff you can say there. All right, this video got on a little longer than I intended, but watch it on double speed. And hopefully this helps you because, kids kind of struggle sometimes with the first couple labs. And hopefully this was worthwhile to get you going in the right direction. Okay. All right. Well, anyway, good luck to you. Thanks for paying attention. Talk to you.